later on. Okay, so without going too much further, I am going to hand over to Jacob, and he's going to kick off our first talk for the day. So Jacob Lister is he's a telecommunications engineer and a kind of signals processing expert, and he's come down from Wellington to present his Noisefloor app and library, which is he will go into a lot of detail about real-time audio processing in the browser and Golang synthesis, and I think it's kind of interesting. This isn't actually the first time that Jacob has brought some music to LCA, but I believe the previous time it was an acoustic guitar. Is that right? Yeah, so we've kind of ramped up the technology spectrum today. So everyone give a big round of applause for Jacob. Thanks.
Thank you very much. Thanks, Mike. Okay, here we are. Okay, let's behave. That's the one I'm going to want. Right, here we are. Oh, good morning. Thanks for that actually quite correct introduction on all fronts, Mike. Yeah, I'm Jacob. Yeah, a little bit about me. I live in Wellington. I'm married with one cat, which is kind of cute. I've done some of these things, embedded systems development and real-time systems, SCADA engineering, a little bit of graphics, telecommunications, network engineering, data science, which is a bit new. Of all those topics, one of my long-term interests as a sort of hobby and side project has actually been music technology and synthesis and this kind of stuff. And of all those experience areas, this one here, embedded systems development and real-time systems, has been probably the most directly relevant. So some of that experience as it's related to real-time systems we're actually dealing with for live performance when you're using a musical instrument, playing a guitar or a keyboard or something. We're dealing with very short timeframes down to the millisecond realm, and having a system which is both correct in its output and also responsive so that it can actually deliver those outputs in a timely manner is quite a challenge. So a little bit of background on the project that I'm currently working on and where it came from. Many years ago, I wrote a software sampler and looper. It's quite an aging project now. The original source base is C and C++. It's looking quite long in the tooth. I have intentions of basically re-implementing the software in some newer technologies, get a bit of experience there, and also make them a little bit more accessible. So I wanted to just run that software briefly so I can show you a little bit about what it's about. In a performance context, I'd normally have a guitar. I would play a section of music, it would be recorded, it would be repeated in a loop, and then I would play more music on top of it. No guitar today, but I have a pre-recorded section. So you can just see a little bit from that interface. Those red blocks are recording sections, greens are playback, and these little blue checks there are just basically a switch of tracks. So I might be moving from a clean sound to a distorted one or something like that. So I'm just going to play that and let it run for a little bit. Looks all good. Right. Right, that looks like it's going to check out just on a, oops, no, a little bit more sound than we wanted. Right, it's going to stop now. That's perfect. That's good timing. Okay, so a little bit of that's a little bit of where I've come from. Where I'm going with this is basically upgrading and re-implementing it in new languages, and I wanted something that could be a little bit more sort of kind of shareable. So the question I started asking myself recently is, could I actually do this in a web environment, have an application which could run in the browser, meet some of those real-time delivery goals, and still be useful, but just be quite shareable. So when you have an application and you're asking people, well, hey, I've written this cool thing, do you want to have a look at it? Asking someone to download this application from the internet, install it, configure it, set it up, it's actually quite a big ask. For yeah, a little thing, but if it's just click on this link and it's in the browser and you can view it, that's a lot more accessible. Other sort of goals there are actually just learn some new technologies. We'll be getting to Golang, which is the actual implementation language, transpiled to JavaScript shortly, and just also that as a hobby project, it's unconstrained by time and deadlines, so basically, I can just work on this until I'm satisfied with it. I don't have a customer or a boss who's needing it. My long-term ambition for this project is DSP Playground. This is a piece of software called Reactor. It's really cool. It basically lets you have all these little quite simple modules of audio processing and just wire them up in a graph and play with it. So obviously I'm nowhere near that stage yet, but that's the great ambition. So why do I think web technologies are actually now appropriate? Well, probably the main thing is just how far those JavaScript interpreters and just-in-time compilers have actually come in recent years, which is they've now actually got performance which is on par or close to what you can get with native code compiled in C. And also just doing that in a very interactive environment where basically you're downloading that application, compiling it on the fly and running it, which gives a lot of possibilities. The second thing is that there's another way that I can actually run this, which is in the browser works pretty well, but it's a bit constrained. But the Google V8 engine, which is what powers the Google Chrome browser's JavaScript, is an open source project. You can download it and compile it and actually build it. And that actually gives you a lot more opportunity to get those really tight real-time deadlines met and have something run that you can actually use quite interactively. I see the problem. Right, this is nothing but just a very simple example of audio processing running in the browser. There's a simple on-screen keyboard. I can just press the keys, hear the notes, and that works. I mean, that's something I can just put on a website and share around. Obviously, it needs to be fleshed out a bit before it's a bit more interesting, but it proves it can be done. And that will be that. Moving along, I'm just going to talk a little bit about how that audio processing, making those notes, is working. This is kind of my reference implementation, which I call the minimum viable synthesizer. So there's some basic fundamental building blocks that are used in audio synthesis, and probably the most important one is the oscillator, which produces a tone of a given waveform at a given frequency. The other things that you kind of need to actually start that sounding interesting and sounding a little bit like an instrument is a thing called an envelope generator, which basically shapes the level or the volume of the sound over time. And this one here is the classic ADSR, attack, decay, sustain, and release. So most instruments, when you hit them, they get to the loudest point quite quickly, and then they start sort of tailing off. So you set that oscillator up to build them. The final component to tying all that together is just a simple gain, which is basically taking that oscillator input in the envelope generator and just attenuating based on the gain. Why am I doing this crazy thing in JavaScript? Because every time I've sort of talked to people about this and said I'm doing this, I get two responses. The first is, that's really cool, and the second one is, you're crazy. So I'm kind of cool with that as a hobby project. Here is why I'm interested in Golang as a implementation language. JavaScript I find a little bit raw, especially for building anything really large. I'd like something which is a bit more sort of type constrained, and there's a bit better, there's tooling around it and all that. But the other reason that it's really quite interesting is that I can compile it to native code, but I can also transpile it to JavaScript. So I can actually do a reference implementation if I want to get really down to the middle and actually have it in a systems programming language. I can just do benchmarking on and actually just see how good I'm getting with the performance that I'm doing. This list of languages here is just kind of a very rough approximation of what's the most sort of system programming language versus what's the most kind of high level. And I sort of see Golang in this nice kind of midpoint where I can kind of go down to system programming languages, and I can kind of go up to high level languages. So just a few sort of tips and tricks here about, or just general advice for getting good real-time performance out of any audio application on Linux. The important thing here is that these real-time applications, they're really down as the kind of performance demands where you're really wanting about under 5 milliseconds of latency between impulses that you're playing on a musical keyboard or so forth, and hearing the output or hearing the noise. And that's quite a tight deadline. But just for some relative comparison, I've just introduced that reference of gaming, which is just because it's a common application, which is getting close to that same territory. But 100 frames a second, just by reference, is 10 milliseconds a frame. So, general commodity operating systems are actually getting close, but, not quite. And so you just need that little extra performance to actually get good real-time performance for music. So here's just a couple of things that you can do, and are very good ideas that will help in the operating system setup. Number one recommended advice is disable Wi-Fi chipsets. They are notoriously bad at stealing resources. Use a low latency kernel. That is becoming less important or significant difference nowadays between a stock kernel, but low latency kernels still definitely have the edge, so it's a good idea to use one. Use a lightweight window manager. So again, anything which is going to sort of steal resources is going to be detrimental to your real-time performance. XFCE is a good choice. And if you want all of those things in one package, Ubuntu Studio is a good out-of-the-box solution because it does, it has all of those above things. So the next demo that I'm going to do is, we're looking at the browser before. Some of the limitations there is that the audio latency is okay, but it wasn't great. This next demonstration will use the Google V8 engine interfacing directly with the audio hardware, and if latency is down to that sort of 5 milliseconds that you want to work with. Another constraint running in the browser is it's possible but difficult to get some external inputs in as well. Getting basic audio out's not hard, but if you want to connect audio inputs like microphones and MIDI devices, it is possible, but there's a fair amount of configuration involved in doing it. So, sounds good. I have a microphone here. This is merely, I'm not going to sing or anything because you'd all leave. But this is merely for demonstrating that there is some audio input running through this engine. It's simply taking the input, applying a simple attenuation filter on a low frequency oscillator. And if I just sort of, we can see that that's working. Simply because it sounds like it's chugging away like a freight train now, I'm going to switch that off. Right. And move on to the keyboard. So again, here I can play notes. I can make a little tune. Like so. That's actually largely what I have in terms of demonstration and so forth. Just given that we have time, I'm going to just get a little bit techie and look a little bit about the software, how it's put together, and what tools are used, and so forth. Right. So the first thing I'm going to look at is just those audio wirings. So the audio API, which is used is Jack. Jack is an audio application server on Linux. It's very popular for this kind of musical applications because it's built around basically building signal paths and connections. So if we look at its interaction, here's those clients which have come up. My MIDI keyboard is connected by this connector into the application itself. And our application is connected to that system output. There's various ways of doing this setup automatically. I prefer to just use scripts. There are some systems which will basically take a snapshot of what clients are running and wire them up automatically. I find them very unreliable. So here I'm just simply running a script. It runs the audio server. There's a function here which just basically keeps trying to make those connections until they ever work or it goes forever. And then it's just simply connecting that MIDI input to the system and so forth. So it's just a nice simple way, and it works well. And it disables the Wi-Fi at the top because that kills things. We'll have a look at some Golang. As I've learnt yesterday, dep is has been the popular way of setting up dependency management in Go, but it is falling out of fashion, and I should re-implement it in modules. My experiences with Go dep have actually been pretty positive. I think I need that. Here we go. So we have our dep file. Things which get a little bit interesting here. I'm bringing in the Gopher JS package, which is the JavaScript transpiler. Why this is a little bit different from importing a regular package is it's actually a tool rather than an imported dependency. So basically you import it and you build it and then you end up with an executable which will transpile your Go into JavaScript. As I needed to make some tweaks to it to sort of get the performance output that I wanted from it, I've modified it a bit. So this is basically a fork on GitHub. So dep actually handles that pretty well. You can basically just fork a project and then specify its origin rather than using the original. Here I've just got some extra libraries related to front end and user interface. So let's have a look at the code. Right, this section is just basically our main processor. So we look right at the top. We have a main processor which is just taking an array of audio samples, an array of MIDI events, and then producing the corresponding samples out as well. So notice here that's actually an array of arrays. Now the reason for that is that it might be a stereo input signal, so you're actually processing on two at once. Here we have our main loop. We're going over every sample. This is just a little bit of processing on that microphone input just to demo that it works. And here, oh, this is interesting as well. Here we're basically taking a MIDI input event stream. So every key that you press on the keyboard is a MIDI event. There is to turn those into working signals that a synthesizer can actually use. Actually might turn to our minimum viable synthesizer. None of the inputs to this are MIDI. The inputs to this are actually trigger signals, which start the various things that have to happen, like the envelope generator running, and a frequency, which is the frequency the oscillator runs. So we need some way of basically taking those MIDI inputs and then turning them into those, in the analog world we call them CVs, or voltages. In the digital world we'll just call them numbers. It's even a little bit more complicated than that because if we want to play more than one note at once, we need some way of actually tracking the state of those various notes. This is an interesting side, but one of the reasons that synthesizers were not polyphonic until really about the late 1970s, early 1980s, is that solving that problem in discrete electronics is actually really quite hard. In digital electronics and microcontrollers, it's actually quite easy. So the reason for that is that there's quite a bit of state to track. So for that reason, synthesizers which could actually generate multiple notes didn't really start becoming commonplace until around the late 1970s, 1980s. Back to the code. That gives us an array of our frequencies. We then feed it into a patch. A patch just does those things that minimum viable sequencer needs, which is an input frequency, an envelope generator, an oscillator, and then sums them up in the gain. And then that's summed up into the output. Right. JavaScript translation. Let's just have a look at the code for one of those processes, like a envelope generator, because that's kind of interesting. So that envelope generator, it's a pretty simple state machine. You know, it starts in that idle phase, and when it gets that trigger, it goes to attack, and then it goes to decay. This is a very simple state machine implemented with just a switch case statement. So on the way up, you know, it's adding things, and on the way down, it's subtracting things, and it's jumping through those various states. If we have a look at the Right, there we go. Transpiled JavaScript. That's, it's actually pretty clean. It's pretty readable. It's pretty close to what you could actually write by hand. So when I started looking at that, I thought, that's viable. I can actually take Go and transpile it to JavaScript and get something which is about as efficient as I'd be able to write by hand. So I need to tweak it a bit to, make sure I get what I expect, but it does work. One of the caveats, though, with the transpiler for Golang is that it does do a lot to give a consistent platform which is highly just consistent with the Go system. And one of the expenses of that is performance. Things like basically sort of type conversions, as the JavaScript doesn't have types, there's a bit of sort of fiddling that goes on when you expose a function in the JavaScript world and then call it into the Golang. That involves some overhead. One example of that, so find out when I've switched off my Wi-Fi, it doesn't work anymore. Yeah, it's probably not. I'm going to decide that's not all that important. So one of the, there's things like, for example, Go has this concept of a slice, which is kind of a view of an array. In the transpiled JavaScript, it will basically put a range check on every array access, which doesn't really make a lot of sense in JavaScript because you're not going to get an exception if you try and read something that's not there. So it's quite easy to actually jump into that source space and switch it off. And many people do it. If you look at their project, it's sort of, several hundred forks and like literally people doing the same kind of stuff. How do you actually tie this into a browser? Yep, very simple harness there. We basically just create that audio context object. The browsers keep changing their policy on what's allowed to make sound and what's not. So you have to do these workarounds that keep changing every year and sort of basically consent that the person using it actually wants sound. Once you've clicked on some object in the browser, then it's allowed to make noise again. Yeah, we're just simply creating an array of samples and they're passing it into our actual transpiled JavaScript. So yeah, nice and easy. And just those general caveats with browser-based audio. It's simple to set up and demo, but it's performance isn't great and connectivity is limited. So you can't really connect MIDI devices without quite a bit of config. So moving on to V8. Yeah, open source and embeddable and implemented in C++. That's actually quite useful because if you really want to get close to the audio, the native audio interfaces, the best way to do that is with C. So because you can actually just write that harness in C++ and the Chrome engines, the V8 engines implemented in C++ and well, that works quite nicely. And it's single-threaded, so that's potentially a limitation. It's an interesting sort of aside to audio processing, which is particularly for DSP, not much of it's actually very parallelizable. So the reason for that is if you've got anything like a feedback filter, your next sample is dependent on the one that came before it, and there's just no way to parallelize that out. The one thing that you can potentially do on sort of multi-core and parallel processing is if you've got an instrument which makes a lot of notes, you could sort of allocate a core to a note, but then there's synchronization problems with that as well because that all has to be brought back together in a hard real-time deadline, which is actually quite tricky. Front end, React, the one true way to write HTML nowadays. In Golang, there are bindings for React. There are lots of them. They all have issues, and my spelling has an issue as well. I'm going to ignore that. Again, they're very hackable. So if we just have a look at the code. Cool. Right, so we can see some, React API stuff here, which is, again, just transpiled into actual JavaScript and used. And those front-end components end up being quite a bit simpler than what they are because they no longer have to do their own update of state change when we get an event. When you hit the key, you want to actually see the color change on the keyboard. So rather than tracking those events and updating the state, we actually just update the entire state of the keyboard and redraw it again. React does its magic as it does. Next things that I want to do with this, the first is actually obviously just cover all the ground that I have in my current existing software sampler and looper. I want to start building this new synthesizer edit module, starting actually. The point where this is going to become quite useful and interesting to use is when I've actually got a graphical editor for this. I can actually just wire these components up and test them on the fly. One other aside from that is that one of the other reasons that makes JavaScript a really interesting platform for doing this is that when we go back to processing, because we're dealing on a sample-by-sample time frame, right, back to our because we're dealing on a sample-by-sample time frame, if we're just doing that in code, it's fine, but if we're actually talking about a graph definition that we're actually going to have to do some basic graph traversal on to actually figure out the dependencies, because one of the important things in the processing is just making sure that all those reverse dependencies are met so that the oscillator and the envelope here are actually ready before the gain's done. So that graph traversal process actually takes more overhead than doing the work of the DSP if it's going to be on a sample-by-sample basis. So one of the really cool things about doing this in JavaScript is because I can compile it on the fly, I can actually basically just build code on the fly and then compile it and actually get it quite efficient. And then I'd probably shoot pretty low for some demos to actually build up first. I'll target the 8-bit era and generate some emulations of classic synthesizers, some C64 SID, some NES 8-bit. And that is where I'm going to go with that. So thank you very much. And yeah, it's been a lot of fun.
We do have time for a couple of questions.
Hey, thanks. My question. Okay, good. My question is, with the graphical editor, do you have any? What are your plans for that? These kind of drag and drop thingies.
Yeah. So that's going to be an interesting question. It's actually quite a hard one to solve in a number of ways. It'll definitely be web-based. I've decided that's the way that I want to go. One of the real complications there is that kind of by necessity involves a back-end, front-end split. So we've got the signal processing going on in the back end, and then a graphical editor in the front, and they're going to have to communicate by some kind of API. And actually sort of splitting those out, it's actually quite hard. But yeah, that's very much what I intend, which will be drag and drop. You just have this palette of processes. In fact, if one of the other things which gets a little bit tricky there. Here we've only got 3 processes, but the thing is when we actually get into the, something useful, there's going to be hundreds of these. So you actually need a way of kind of enumerating them and just having them as quite generic little processing units. So here we've got this little thing called processor factory, and it just takes the name of a processor and it gives you one back, right? But the next thing that's going to have to happen is in these processes, I can put some metadata on them, just saying these are your input parameters, here's what they're called, here's some sensible limits to them, and here's their acceptable ranges. So the idea of that processor factory interface is actually going to give me back a processor where I can just sort of ask, what are your parameters? And it's just going to lay them out, and then you'll be able to sort of wire them up.
And can you give some idea of the performance in the browser as to kind of how many voices you might expect if you implement a synth there?
Right. Yeah, it's a very good question. These ones at the moment, I'm kind of running up to kind of 100 voices just to do benchmark testing, and that's working all right. Now, obviously, that's going to get quite a bit more constrained when the voices become quite a bit more complicated. But it will, it will need to be in that sort of order to be useful. So benchmarking is going to become quite important. And again, one of the reasons I'm quite happy with using Go as a reference language is what I will be able to do is build these up in JavaScript and test them, but also compile down to native code and then benchmark against that. So I'll be able to see quite quickly if I'm on the right track and the way the optimization's working. But yeah, it needs to be hundreds of voices. Yeah. I mean, so some of the more complicated synthesizer methods, such as additive, work by just having a massive number of potential voices across the harmonic spectrum and then building up from that. So I mean, you literally need hundreds of oscillators to make that work.